So this lecture will be recorded today. So if you are not comfortable with your voice being recorded or being on the video, please just send me a chat message. What we're going to be talking about is continuing Newton's laws, and I have more problems to solve, some more difficult problems, and we're going to go over Newton's third law. So we didn't talk about Newton's third law yet, so I'll just, let's do a review problem before I do Newton's third law. So here we go. We're going to do two review problems before we do Newton's third law. If I can get this to work. Doesn't want to work. So I have an object on an inclined plane. The inclined plane is at 25 degrees. The mass of the object is 37 kilograms. What's the object's acceleration down the plane? Give that a try. And then when you, why is this not working? Sorry, those little, remember, give me a thumbs up when you're ready. Let me know. All right, ready? So we have our object here, and oops, I had the eraser on, not good. And this object is going to have a weight, remember, a weight coming down, and that weight is equal to mg. So the weight of our object has two components. It has an x component and a y component. So it's going to have wx and wy. Those are our two components. Wx is the component that causes it to go down the inclined plane. And our angle here will be 65 degrees. So WX equals W cosine 65. Sum of the forces in the X equal MAX. The only fourth direction is so negative WX equals MAX. It's negative because on our Cartesian coordinate system, negative X, there's positive X. It's going in the negative direction. So mg over AX equals 37 times 9.8 times the cosine of 65 divided by 37. Kind of ran myself out of room here. AX equals negative 4.14 meters per second squared. How'd we do on that one? Does anybody have any questions there?
I'm all good here.
Let's review from last time. Yeah. Anybody have any questions? I thought someone said something, sorry. All right, let's try one more review. Next problem is, let's do a little Atwood machine. This is what the Atwood machine, these two pulleys are called. It's called an Atwood machine, if you were wondering. So let's put one pulley on here and another one on here. We'll call this guy A and B. And the mass of A is, I don't know, 100 kilograms. The mass of B is 65 kilograms. Find the acceleration of the system. Again, we're trying this at our seats. Make sure when you guys are doing these problems that you're drawing the free body diagrams. That's pretty key to getting them to be able to see what's going on and getting them correct. right, just to check here, make sure that when you're drawing this, right, A and B are connected. And remember, the weight of B is going against the weight of A. That's how you want to set it up. So the weight of B is MBG, and the weight of A is MAG. So this is 100 times 9.8, and this is 65 times 9.8. So when you say the sum of the forces in the X equal MAX, which is essentially, right, oops, I got the eraser on, which is essentially the same thing as AY, AX and AY, right? This AY here should be AX, right? These two things are essentially the same, right? Because it's going to be going up and down, but we stretch it out linearly, horizontally, so you can see how the forces act against one another. So that's why we set it up like that. But this AX is the same thing as that AY. So our positive force WB is 65 times 9.8 minus 100 times 9.8 equals the total mass, 100 plus 65 times AX. So AX equals 65 times 9.8 minus 100 times 9.8 over 165. And that's how you review. Anybody have any questions on that?
Why is it negative? I did the math and I didn't get it as a negative.
65 is our pot. You can see over here on our right, we have 65 going right here. And we have the 100 one going to the left. Remember our Cartesian coordinate plane. This is the positive X. This is the negative X. 65 is smaller than 100. So that's why it goes, this is telling us that it's accelerating towards A, that this is the direction of the acceleration. Right? That one's going down and this one's going up. That's what a negative tells us. Does that make sense?
It does.
Okay, good.
Will the bigger mass always be the one that determines the direction, like that we write down? Because like
the bigger mass will always determine the direction, but the sign is always from where it's at on the Cartesian coordinate system, whether it's positive or negative. Does that make sense?
So in reference to which?
Like if the B, for instance, in this problem, if the B was, let's say, 400 and the A was 150, would you have a positive or negative acceleration?
Well, if we're looking at A is going upwards. So
Right.
that'd be positive. If we're looking at B, it's going downwards. So it's negative.
Yeah, that's right. That's why we stretch it out, as you can see over here. That's why we stretch it out linearly, or horizontally, I should say, because then you can see how they work against each other, because here one's going up and the other one's going down. But in actuality, the entire system, this green line is rotating like this.
Yeah.
So B is going up, A is going down, but the whole system is rotating what we could say is counterclockwise. Does that make sense? So we just say A is negative, which tells us that the one on the left is going down.
So that would mean that we're now relying on whether we write A or B on the left or right on the graph. in order to determine if we put a negative for acceleration. So which do we put
Yeah.
on the left or right?
Well, just the way it's set up. If this were the coordinate system right here, right, you can see B's on the right side, A's on the left side. So A is being, the force on A and the force on B, is the same. This tension force is equal to each other, that tension there. So essentially, when we look at them, they're stretched out, and A is just coming out here, and B is coming out here. You know, see how I did that? I just flattened
Yeah,
them.
so that'd be left to right then?
Yes.
Okay.
All right, now let's try some new stuff. Those are good questions. Today we're going to learn about Newton's third law. Newton's third law, and it's called action, reaction. Newton's third law is action, reaction. So it says for every action force, there's a reaction force equal in magnitude and opposite in direction. So let's just say we have someone standing here and they get punched in the face, right? This is a punch, a glove. So this is the action force. The reaction force is their force of their head hitting back on the glove. So whatever this action force is, it's going to be equal and opposite to the reaction force. That's Newton's third law. So if I'm standing on the ground, I have a weight that goes downward. The ground is pushing back up on me with an equal amount of force. We call this the normal force. The normal force is a reaction force. The normal force is always perpendicular to the surface. So depending on your surface, if your surface is horizontal, your normal force is going to be up. If your surface is at an angle and you have an object on the surface at an angle, right? We know the weight of the object is down. We know the y component holds it. Well, the normal force is going to be perpendicular to the surface. So the normal force is not equal to the weight. The normal force in this case would be equal to the y component of the weight. Sometimes people get confused and they say, oh, the normal force is equal to the weight, but it's not necessarily true. That's only true when you have a horizontal surface, and those are the only two. Let's say that we're applying a force against the wall, right? The normal force then would be coming back off the wall. So the normal force is always perpendicular to the surface. That's the one thing you need to remember about the normal force more than anything, is that it's perpendicular to the surface. Sorry to get that on you. So for Newton's third law, we're going to be solving for these normal forces a lot of times. Any questions on that? So we got the first law, which is inertia. Second law is net force equals mass times acceleration. And the third law is action reaction. Those are Newton's three laws. So let's try a problem here involving the elevator, like in the homework. All right, let's say a person is riding in an elevator and has a mass of, I don't know, 87 kilograms. What is the acceleration? Oh, no, that's not what I want. Sorry. What is the reading on a scale if part A, the acceleration in the y equals 0, part B, the acceleration in the y is positive 2 meters per second squared, and C, the acceleration in the y is negative 2 meters per second squared. So what's happening here is there's an elevator and there's a person standing on a scale. The person's weight is downward. The normal force is upwards. In each case, there's a different acceleration. What we want to do is we want to find the acceleration for each scenario. We have two opposing forces. The scale reading is the normal force. This is a scale reading. That's what the normal force is, your scale reading. Your weight is not going to change. Your weight is always mg. So your weight here is 87 times 9.8. $852.6 newtons. So that doesn't change. So let's take a look at how we do this. The formula is Newton's second law. Sum of the forces in the y equal MAY. We have two forces in every scenario. N minus W equals MAY. In the first scenario, part A, AY equals 0. So we have N minus W equals 0. N is going to equal 852.6 newtons. In the second scenario, now AY is plus 2 meters per second squared. So in this one, we have N minus 852.6 equals 87 times 2. N equals 1,026.6 newtons. In the third scenario, now we have negative 2. So it's 852.6 equals 87 times negative 2. And in the third scenario, there's a point in there. Is 678.6.
Is the
So you
scale
can see you
reading
get three different forces acting on you from the scale. Your weight apparently changes by the scale reading based on the acceleration of the elevator. When you're going up in an elevator, you feel heavier. The floor is pushing up on you, making you feel heavier. When you're going down, the floor is falling away from you, so you feel lighter. If the floor were accelerating downward at negative 9.8, you would feel weightless. That's where weightlessness comes from. Because if the floor is accelerating downward at negative 9.8, right, you would have N minus 852.6 equals 7 times negative 9.8. Well, those two cancel out. Your normal force would equal 0. and you're going to. So this is a fun problem. Does anybody need anything clarified there? Anything you didn't quite understand?
I don't see how the algebra works out that way. Like I would think that if you do n minus 852 equals 876, that n would have to be like 1600 something or 1700.
Where, over here in the green?
With B.
Over here? Well, what's this? 156?
It's written in black.
Right here,
it
where
could
I wrote
be
in green.
any one of these.
So here you have, when you take this, you have to add this to both sides. So you end up with 852.6 plus 156, and that's 1026.6. That's your newtons.
Wait, don't you have to add 852.6 to the other side?
I did right here, and they cancel out to 0. And that gives you n by itself.
But 876 plus 852, that's a pretty big number.
Where's 876? Where are you seeing 876?
Wouldn't that be how you'd have to solve for the opposite side, the right side of that equation?
Well, what's 87 times 2? Not, oh, it's 87. That's 174, not 156. Sorry. That's 174. 87 times 2 is 174.
Oh, it's 87. I thought that was like.
It is 87.
I thought you wrote 876.
Mass. It's the mass ratio.
What's that?
Do you see it now?
Huh? What character do you have next to the 87?
This is just a parenthesis.
Oh, okay.
It's just 87 times 2.
Oh, I couldn't see it because it was off your screen. No, I thought you were
It's
doing.
not on the screen?
I thought that parenthesis was like a 6.
Oh, no, sorry. It's 87 times 2. Can you see it now?
No.
You can't see this whole screen on your screen?
I can, I guess.
You can?
I can.
I hit escape and I just moved the list of people away from it. I can see it now.
Ah. All right, good. So
I have a question about the problem. Is the scale measuring in newtons?
yes.
Okay.
Now we want to do it in pounds. We have to do like the factor label to convert from newtons to pounds.
Okay. And pounds is a unit
English
of
unit.
force, not a unit of mass, right?
Yeah, pounds is a unit of force. That's good.
Okay.
All right, let's try another one. We're having fun now. So in part A, what force must be applied to keep the book at rest? And part B, what is the normal force? All right, and here's a picture. Let's go with the wall be blue and our book will be green. So we're holding this book against the wall and we're applying a force at an angle of 55 degrees. So Can you do this on your own? Give it a try. Give me a thumbs up when you think you got it. Actually, just draw the free body diagram. When you get the free body diagram drawn, give me a thumbs up. I want to see if you can get this free body diagram drawn correctly. And for those of you, the free body diagram is the picture representing the forces. We'll call this force here F. Thumbs up when you think you have your free body diagram drawn.
Could you go over what that is?
The free body diagram?
Yeah, I haven't.
That's the forces, like this picture up here, or like this picture. These are free body diagrams that show the forces acting on the system. If you don't know, just chill out. I'll show you here in a second. All right, so what the free body diagram should look like is this. You should have, I'm just going to erase this because I have limited space. You have an X component of F holding it against the wall. F cosine 55. This has a weight. It has a Y component, F sine of 55. And you have a normal force. And the mass is 5 kilograms. How do we do on our free body diagrams? Did anybody get it right? Thumbs up if you got that right. Nobody? Come on, somebody. No? I'll give a frowny face. Oh, one person. Good. Whew. Saved me. Now, we have to find two things. We have to find what force must be applied to keep the book at rest. That force is F. So our Y component, it's at rest. So that means we're in equilibrium. So the sum of the forces in the Y have to equal 0. Weight, remember, is equal to mg. Weight is equal to 5 times 9.8. Weight is equal to 49 newtons. So we have F sine of 55 equals 49. F equals 49 divided by the sine of 55. 59.82 newtons. That is the force in part 1 that keeps the system at rest. 59.82 newtons. Any questions there before we move to part 2 or part B?
So with the 3-body diagram,
Yeah.
So those F sine and F cosine, are those, are you talking about the X and Y of the force that you're applying holding it there?
Yeah, this was the original force F at 55 degrees. Those are the components.
Right.
Right, so we have Fx here and Fy here.
Yeah. And
Yes.
in order for, okay, so the top and bottom force would have to be equal. Well, all of these are equal.
Right, it's an equal.
Well, like if that would only be true because we know it's being held in place, right?
Yeah,
Otherwise, the
some
book
of the
would be
force, because
accelerating
it tells us in the given that the book is at rest. So if you're applying a force less than 59.8, right? If your force is less than 59.82 newtons, the acceleration is downward. If your force is greater than 59.82 newtons, you have an upward acceleration.
Yeah, and would we want to draw that in a way that would show it as equal, although that might involve more things than we can really draw.
Well, we're just drawing the forces. We just want to represent the forces acting on it.
Yeah.
We don't want to get carried away with our drawings. This is AX, by the way. I screwed that up. So in the X direction, we have a positive N, right? It's going to the right, minus F cosine 55 equals 0. Again, it's no acceleration in the X, it's at rest. So N equals 59.82 cosine of 55. $34.31 newtons. So that's our answer for part B. Questions on that? All right, I got 3 more problems to get through here that I got planned for us. Let's go to another screen. The next problem, a rocket ship of mass 1,000 kilograms blasts off with a thrust force of 20,000 newtons. What is the acceleration? All right, to draw a free body diagram of this situation before you solve it. Give me a thumbs up when you think you have it drawn correctly. All right, that's about half of you. Spike. We got the weight acting on it, 1,000 times 9.8, 9,800 newtons. We got a thruster force here. I'll call this F, 20,000 newtons. We want to find the acceleration in the Y. So we say the sum of the forces in the Y equal MAY. F minus mg, which is W, equals MAY. 20,000 minus 9,800 divided by 9,800. No, I screwed that up. The mass is 1,000. Sorry about that. Divided by 1,000 equals AY. I got 10.20 meters per second squared. Not very high acceleration, 1G. Really a little thruster, more thruster force. Anybody need it clarified there? I think there's one in the homework like this. So hopefully you did
But
those.
that would still feel like 2G to someone riding it, right? Or a little higher.
Well, it would feel like 1G. Not very much.
Wait, why?
Because you already took into account the weight.
I mean, like, gravity's already pulling on you, plus the fact that you're accelerating upwards.
Well, your first gravity's canceling out, or your first G is canceling out gravity, and then you're experiencing 1G on top of that. Does that make sense? Because that's what our subtraction right here is.
I just meant in terms
All right,
of like,
let's try another one. What's that?
it's not important. Don't worry about it.
All right. I'm just going to draw this one for you. It needs to be 1,000 newtons. 1,000 newtons. We call that force of friction. I want you to find two things. One, the acceleration in the x. Two, the normal force from this here problem. Is the free body diagram complete right now? Simple yes or no, anybody, somebody. Is the free body diagram complete right now? Yes or no, somebody? I'm gonna keep asking.
This is on a surface. I don't really know what the exact question is.
The picture that I have drawn, is that an accurate representation of all the forces acting on the 25 kilogram mass? It's on a surface, yeah, it's getting pulled down the street or whatever, I don't know, through the grass. But is that an accurate representation of all the forces acting on it?
Well, there would be the gravity and then the normal force.
There you go. So the answer is no, right? It's not a final picture, right? We have the
Right.
weight, we have the normal force, and this has to get broken into its components. So now solve it now that I can help you out there.
Would it be 1,000 sine and cosine 30?
Oh yeah, thanks. I don't know why I had 100 in my brain.
Is that 130 degrees as in like 40 degrees, or is that 130 degrees relative to a
It's
straight
That's
line?
not
It's
100.
just 30,
That's
it's
the arrow, the whatever that's called, even the marker for
Oh,
the
okay.
degrees. When you think you got them, give me a thumbs up. Good, good, good. All right, let's take a look, see how this one's done. We'll do AX here. So we do the sum of the, I'm going to try and sum of the forces in the X equal MAX. We got two forces. We have 1,000 cosine 30 minus 75 equals 25 times AX. You guys know why the negative is with the 75? Is there anybody who needs clarification on why I did that? Why I subtracted it? Good. So 1,000 cosine 30, 75 minus 25 divide. The acceleration is 31.64 meters per second squared. Pretty big acceleration here. N plus 1,000 sine of 30 minus 25 times 9.8 equals 0. The acceleration in the y is 0. It's not being pulled up into the air. Or is it? It definitely is, isn't it? Oh, son of a gun. I made the force too big. I knew 100 newtons was the right force. Oh, but anyway, this is how you would do it. We're going to get normal force is equal to negative number. 25. Negative 255. You know you did something wrong if you get a negative normal force. So I made this, my bad. Sorry about that. Sometimes when you make these numbers off the top of your head, you don't see it right away. All right, we're going to add a step 3 this. Step 3. F accelerates for 15 seconds from rest. How far does it travel? Oh, a little flashback to last chapter. If it accelerates for 15 seconds from rest, how far does it travel?
In what direction?
What do you mean?
X or Y?
Oh, well, we're not doing.
Or
Yeah,
both?
disregard this in the X direction. We're assuming that
All right.
it was not accelerating in the Y.
Yeah.
Remember how to do this? Right? V naught equals 0. V we don't know. A is 31.64. T is 15 seconds. X naught is 0. X is what we're solving for. X minus X naught equals V naught T plus 1/2 AT squared. This is 0. This is 0. X equals 1/2 31.64 times 15 squared. .56 or 3559.6 meters. That's how far we traveled. Does anybody have questions on this?